Great. So welcome to a focus today on powdery mildew. I'm Melissa Hanson, the Research Program Director for the Washington State Wine Commission. The Wine Commission and Washington State University, we partner together and put these WAVE or WAVEx's together. WAVE stands for Washington Advancements in Viticulture and Enology, and they're designed to really drill down to the research results and help make that connection between the research and the industry. And we like to do these in person. Hopefully next year we will be, because then it also gives industry growers and winemakers a chance to visit and get to know their researchers. But one of the great things about Zoom is that we can bring in somebody from out of state. And so I'm really thrilled today to be able to feature Dr. Michelle Moyer and Dr. David Godowry from Cornell University. I'm going to introduce both of them now, and then Michelle will be first, and then she'll hand it over to David. And first, some real quick little housekeeping. You guys probably have this memorized by now, but just as a reminder, put your question and answers in the Q&A. Don't put them in chat box because everybody can't see the chat box. And we will be recording this, and all those who registered will get a link, and the Wine Commission will also have the recording link on our website, and it'll be publicized in our newsletters. And then just a plug, the next short little focused webinar is July 14th. We saved the summer months for more of the winemaking focused research, because growers are quite busy. So it will be working with high pH wines. Dr. Thomas Hinnett-Kling just finished up some research on how to work with high pH wines and keep the wine spoilage out of them. So you can go to the Wine Commission's website to register. And then just our little plug here. So with that, I'm gonna stop sharing. And as I stop, so Michelle, if you want to start to pull yours up. Michelle got her BS from the University of Wisconsin, and then she went to Cornell to get her PhD in plant pathology and studied underneath Dr. David Godowry. So we have a nice little connection here. Michelle's the Associate Professor and Extension Viticulturist, and she leads a national research project on powdery mildew and fungicide resistance. And she's going to bring us up to date on frame fungus. You'll see that spelled out here in her slides. And she also spends quite a bit of time on nematodes and phylloxera. So with that, Michelle.
Sorry, I'm sorry here. We're having a little bit of a challenge. Let me know if you actually can see my screen.
I did stop sharing.
Here, I'm going to try again. There we go. It's just being silly. It's all me, Melissa. It's not you. Trust me. Can you see my screen?
Yes.
All right, perfect. Thanks to you, everybody. So I am very excited here today to actually be able to present with David about various things all related to grape powdery mildew. So I did have the wonderful opportunity and chance to work with David for about 5-6 years back in the early 2000s. And so it's fun to kind of come full circle. So today I'm going to have just a little bit of a preamble. Most of today's show is dedicated to what David will be presenting on UVC light and grapevines, but I wanted to give folks who are attending a chance to have a quick update on what our program is doing related to fungicide resistance management. And then of course, what we are doing to help assist David with field trials and evaluations related to managing powdery mildew in grapes using UVC light. So quick, obviously everybody knows I like to do fun plugs, and the big thing related to powdery mildew, obviously our main management strategy is still pesticide-based or fungicide-based applications or sprays. For those who do not already know, frac, you guys should know what the word frac is. You've probably heard me say it way too many times. But the FRAC organization has developed a really nice smartphone application that you can download that allows you to search by fungicide branding or fungicide active ingredients. And it provides all the information that you would need to know on the resistance of that particular FRAC group, cross resistance within that frat group, et cetera. So it's a really nice supplementary tool to have when you guys are writing your spray programs or evaluating your spray programs that you're receiving from another person. So that's my quick plug. So visit frac.info to download that application. I use it quite a bit. It's a pretty nice, very intuitive app. So really the point of the work that my program is currently focusing on, and obviously the discussions that we'll be kind of touching on today relates to product stewardship, really. So how do we think about the future of disease management when we start to lose tools? And that's what fungicide resistance is, right? It's the loss of potential efficacious tools that for field application. So the work that we're doing on is looking at that is, one, how do we keep products on the useful and in our toolbox for a longer period of time? And then what do we do when we inevitably lose those products for various reasons? So first, a quick update on FRAME. So as Melissa mentioned, that's a large federal project I'm leading called, it's titled Fungicide Resistance Assessment, Mitigation and Extension Network for Wine Table and Raisin Grapes. And really the premise of that particular project is monitoring for fungicide resistance in grapevine powdery mildew, and then hopefully working out some strategies to help improve spray program design to reduce field level control failures related to fungicide resistance. The primary focus is on looking for FRAC 11 or the strobilurine resistance in grape powdery mildew, but we are also working on FRAC 3 resistance monitoring, FRAC 7 resistance monitoring, 13, et cetera. So we're trying to build tools for those. But most of you are familiar with our rapid testing. So I wanted to provide a quick update on what we've seen so far. So with the Wine Commission and with this FRAME federal SCRI project, we've been monitoring fungicide resistance in Washington State since 2017. And so what you're seeing here in these pie charts are the percent of the samples that you all have submitted to my program for evaluation that have come back resistant in red, sensitive to FRAC 11 fungicides in green, and then kind of a mixed population where there were some resistant isolates and some or individuals and some sensitive individuals. So back in 2017, we got a lot of samples from you guys. I think 2016, 2017 were kind of the early years of some potential field level failures with mildew. So a lot of samples were sent in. We had about 250, and most of them came back as resistant to FRAC 11 fungicides. So obviously pretty concerning. Our sample size has gone down over the years, and part of that's because you guys have been excellent at mildew control. I think we really hit things hard between 2017 and 2018, and we are seeing the results of that. So the big take home here that I wanted to emphasize is the number of samples that we are getting back right now that are resistant to FRAC 11 fungicides is going down. So the proportion of those are going down, which is a really nice positive sign that we're either doing a much better job controlling mildew, period, so we're just not detecting mildew in vineyards, or that you guys have also done such a good job switching up, pulling FRAC 11 fungicides out of your program, or only using them once, or only using them with tank mixes, that we're really starting to see that proportion go down. And we also know you have responded to some of our pleas to back off on the FRAC 11s, because since at least over a 2 to 3 year growing season period, we've seen a decrease in FRAC 3 and FRAC 11 use within our state in terms of number of applications. But what concern, and obviously subsequent uptick of sulfur use, so clearly folks are tank mixing. But what we have seen is, instead of using FRAC 3 and FRAC 11 fungicides, you guys are switching to FRAC 7, FRAC 50, so that's Vivando and Prolivo, and FRAC U06, which is Torino. We're starting to see an uptick in the number of those applications, and especially in 2019 and 2020, we're really starting to see jumps of folks just not using FRAC 11s or 3s at all, and then really heavily relying on the FRAC 50 and the FRAC U06. So I do want folks to be conscious. If you are using things like Prolivo, Vivando, and Torino in your vineyard, they're excellent products. Don't use them more than twice in season. In fact, if you can, just use them once, each one of those products, or FRAC 50 once, a FRAC U06 once. That's really what we would like to see happen, because these are products that have seen fungicide resistance in the European Union area. So there is the risk there. So just be careful. They're great products, but when we switch overuse of one thing to another, it's still an overuse. The other thing we've learned over the course of FRAME, or this FRAME project, is that We very rarely detect FRAC 11 resistant isolates early in the growing season. And in many cases, it's actually very hard to detect mildew in the field in a normal commercial setting, much before pre-bloom and bloom. We usually, when we find sensitive isolates, we usually pick them up at post-fruit set to bunch closure, but by the end of the growing season is when we really start to see a lot of FRAC 11 resistant isolates. We're not necessarily entirely sure why this might be the case. There might be some fitness cost or advantage that allows selection for those resistant individuals to thrive towards the end of the season. It could also very much be related to the fact that a number of the botryticides that I think a lot of us like to use out here in Washington tend to have a FRAC 11 product in it. So we're increasing the population of resistant isolates that would have already been in the vineyard, perhaps kind of developing around here at this time. But the key take home is you guys are doing great and rotating things up, and we're starting to see a reduction in the number of FRAC 11 resistant isolates. So that's a positive thing. So with that, if you're like, but Michelle, I never sent you a sample and I would love to have free testing before WSU starts charging you for it, I say, excellent, send me an email, or actually send my project manager, Charlotte Oliver, an email, and we can actually ship out some sampling kits to you. It's a quick glove and swab method. I think many of you guys are familiar with shoving swabs up your nose at this point. It's the same thing. You use the same tool, except you rub it on a leaf surface. So much less invasive than a COVID test. So you just send that back to us, and if we receive samples by a Monday, you'll get your results by a Friday. So it's a really quick turnaround. And the beauty of this potential technique, we have more information if you are interested, is some folks are actually using it for presence and absence sampling. So we can actually use it to detect the presence of mildew in addition to detecting the presence of FRAC 11 resistant isolates. We've also run a bunch of numbers and have come to the conclusion that from a commercial standpoint, there are some labs that do offer FRAC 11 fungicide resistance testing commercially. What will likely happen at the end of frame when these, and because it's a very simple test to do, but it's not cheap, the likely cost of these things will be about $50 to $75 a unit, depending on where you're located, because there is some cost savings with doing large sampling. So just so everybody's aware, but until 2022 of August, you can get your samples tested for free. So I would recommend doing that. So again, Charlotte Oliver's email address is right here. I'll actually put that same email address in the chat box when we are done, so you guys can access and email Charlotte. And again, these are for folks who are in Washington. If you're elsewhere in the country, just let Charlotte know and she can connect you with another person within the United States that can provide a sampling kit for you that's closer to your area. Again, I do want to direct folks to our Frame website. We have lots of resources and information there. Just kind of an overview of what you can see. It's at framenetworks.wsu.edu. And most importantly, when you guys are sending us in your fungicide swabs, we'll actually send you back a decision tree that will tell you how to adjust your spray programs depending on what the results are of your testing that's coming back. So if you have sensitive isolates early season versus resistant isolates, how might you be able to adjust your program if you have FRAC 11 fungicides that are in your current rotation? How might you better be able to use them? So this is a new tool that you guys can download from our Frame website at this time. We also, keeping on my bad COVID joke theme, have a FRAC 11 resistance dashboard. So this is modeled off of the Johns Hopkins dashboard. We will be updating this throughout the 2021 growing season, but you can access it from our website, and you can actually see which states have what levels or proportion of resistance in their mildew isolates. And we also can do it across grape type, wine grapes, juice grapes, hybrid wine grapes, vinifera wine grapes. So it's kind of fun to poke around for those who really like to look and to monitor data. So that's available from the Frame network as well. So into the important and fun parts, so we can get David on screen. The other thing that we like to do, so obviously fungicides are heavily used for mildew management, but clearly resistance is a challenge. So what are some alternative approaches that we can do to manage mildew that is not necessarily direct chemistry? Well, it's chemistry, but not necessarily a direct spray application in the traditional sense. So our program, in conjunction with several other folks here at WSU, many of you are familiar with Love Coat and Gwen Hoheisel, we are the sprayer team, and we've been working on a number of alternative pest management projects across tree fruit and grapes. Lexi McDaniel, pictured here, is our PhD candidate working on the grape systems. And so we're working on a series of machines that are considered no residue spray programs for tree fruit and grapes, including a heated oil or oil thermal therapy using field evaluations of ozonated water. They don't work very well so far, but we're working on that. And then of course, UVC therapy. So we're using the term therapy because I don't like, we're calling them sprays, and obviously they're not sprays, but yeah, UVC therapy. Lexi started our UVC trials last summer, working on essentially two major things. And I think David will go into more of the details of how UVC works, but because that's all been worked out or is in the process of being worked out. But our main goal here through the Washington State Wine Commission was to work on timing, just like we do with our fungicides. When can we use UVC to its best ability in our systems? And then intervals. So how frequently would we have to do UVC therapy treatments to achieve some or totally commercially acceptable levels of disease control? So we did these two types of trials, working on trial one, where we're just replacing early season sprays with UVC therapy. And then we did another trial where we did UVC therapy all season long, looking at 7-day intervals and 14-day intervals. Unfortunately, it was a very low disease pressure situation in our vineyard last year. Even looking at foliar disease, our canopies at most hit about between 17 and 50% of foliar severity. So I mean, is relatively high. But even our grower controls had relatively high mildew in the canopy, because I don't treat the canopy. I don't design our grower control sprays to manage foliar. We manage the fruit. And if you look at our fruit disease, and David will probably cry a little bit on what untreated controls look like in terms of total disease severity here, between 0.6 and 4.8% cluster severity. So extremely low disease severity. But even with that very, very low disease pressure, which often makes it very hard to distinguish how treatments are going, we saw some really nice trends where a 7-day UVC interval was giving us pretty acceptable levels of control. It wasn't quite as good as our total season long spray grower control, but they were performing better than our unsprayed control. So we saw that, liked that type of data, and then have switched our treatments for this coming season to be reflective of some tighter intervals. We are also looking quite a bit at fruit quality. So we are measuring tannins, phenolics, and basic harvest metrics for the fruit, just because we are interested in seeing, and this is on Chardonnay, if the UVC, especially season-long treatments, have a potential negative impact on fruit quality. In addition, Lexi is monitoring these sites, because I do have, just like the rest of you, I have FRAC 11 fungicide-resistant populations in this particular block. And we are monitoring to see how UVC continuous treatment is affecting that population. We're still working on the data from that, because we had some lab restrictions due to COVID that slowed down that data processing. So for this summer, we are continuing our UVC trials. We have a brand new unit that Lexi has worked with Vinetech equipment to help us build out. It's on a 3-point hitch, beautifully easy to mount and easy to drive. So I know Lexi has appreciated that. And kind of continuing both our interval and timing type trials. So looking at using UVC as a replacement for kind of our pre-bloom sulfur sprays, and then switching to grower controls for the rest of the season. And then looking at a tighter interval schedule for more effective disease control. So comparing a twice-a-week UVC application to a once-a-week UVC application, and relative to an untreated control in our conventional spray control. I am including the dose that we're doing down here, which is 200 joules per meter squared, because David will discuss kind of some of their trials related to how much UVC you need. So this is just a number for folks to know that we are evaluating a higher dose in our particular trial. And again, we'll be monitoring foliar and fruit disease progress throughout the whole season, and doing kind of an end of the season rating as well. We are continuing to monitor effect on fungicide resistant population. And then Lexi is also expanding that kind of fruit quality data to potentially incorporate an effect on fruit sensory. So if we can't chemically measure changes in the fruit composition, is there a sensorial or a sensory shift that might impact picking decisions, or how folks might want to use that fruit further on in wine processing. But I didn't want to take up too much time, because everybody is here to listen to David and hear all the great things that he has done leading up to the UVC trial. But I just wanted to let folks know that we are taking the tools that David has developed out at Cornell and doing some field application here to see how we might be able to get them to fit within the the Washington State wine grape production system, because our weather is a little bit different than upstate New York.
Thank you, Michelle. There's one quick question.
Yep.
Would you want samples from a no pesticide vineyard?
Absolutely. Yep.
Okay, great. So Paul, send them in.
Mhm.
And I was, in my excitement, I didn't give you a little background on David. He's an East Coast guy, graduated from New Hampshire in plant pathology. He's been at Cornell since 1985, working on fruit diseases, powdery mildew, downy mildew. And he'll give you the full scale of his UVC, but this is one of those things that he worked on about 20 years ago, put it aside, and then it came back to life recently. So sometimes things aren't ripe at the time, but they can get better in the bottle. And I think maybe hopefully this is one of those things that got better in the bottle with a different look and different approach. So with that, David, why don't you pull your screen up?
Okay, let's see if I can still remember how to do screen sharing. Start this first, and then share screen. Is this working?
Perfect.
Good.
You're up.
All right, that's a load off my mind. You don't know this, but we showed up 45 minutes early, mostly because they were worried. I was worried about my ability to manage screen sharing. You would think that after 14 months of living on Zoom, I would be able to do this. It's not true. So thank you for having enough confidence in me to take a chance on me actually being able to talk to you. So thanks to the organizers for inviting me. I want to talk to you about where we are in the research on the uses of light to suppress plant diseases in general. Now, some of you might have heard about this work on grapes and other crops. It's been in the news a lot lately, especially on strawberries. What you might not have seen is the overall scope of the project, which involves test sites on diverse crops around the US and as well as overseas. This is a big project. My job is really to function as the kind of the chief cat herder for a team of scientists that's spread across several institutions, countries, and corporations. So much of what I'm going to be presenting today is actually work that was conducted by other members of the research team, both in the US and overseas. As the project coordinator, if you're interested in the peer-reviewed papers in the area, popular articles, the posters, contact information for the various investigators, videos, educational resources, visits to some of the training sites when that becomes possible, collaborative opportunities if you're interested in taking part in the trials. I'm happy to provide that information, so please contact me. So I want to start by trying to put this work in perspective. Now, microbial pathogens have been attacking plants for a very long time. They have a huge head start on humans. They've become pathogens over an evolutionary scale of time amidst endlessly repeated cycles of light and darkness. Now, in this time, these simple one-celled microorganisms have evolved to the point where they can sense, they can interpret, and they can use light to direct their development. Now, the general area of light and plant pathogens is really broad. There's a lot of people working in that area. I'm going to today take just one of those evolutionary traits, and we'll see how we can use it against a pathogen. And that one trait is how they deal with ultraviolet light. Now, above ground pathogens live in a world that's bathed in sunlight during daylight hours. Ultraviolet light is a natural part of the solar spectrum, and it causes damage to a pathogen's DNA. Now, despite the occurrence of that damage, pathogens can survive and thrive in natural solar UV because they possess systems that can repair the damage to that DNA almost as fast as it occurs. Those DNA repair systems are actually driven and recharged by blue light, so they don't operate during darkness. And that one simple fact is the key to using UV successfully to suppress a pathogen. Now, a real breakthrough occurred in the work about 10 years ago when a PhD student named Rupalai Suthaparan, we were working with him in Norway on the research team there, discovered that applying UV light at night was much more effective in killing powdery mildew on cucumbers than it was during daylight. In effect, applying UV at night bypasses the pathogen's ability to repair the damage to its DNA. That discovery alone allowed us to use about 10% of the dose of UV that would be required during daylight to achieve the same degree of disease reduction. So we now know that nighttime UV applications are similarly more effective against many pathogens and at a dose far below what would cause damage to the plant. Now, you can read about this biochemical and genetic aspect of this phenomenon in excruciating detail. The bottom line for practical purposes is that pathogens such as powdery mildew, which is shown here, and many other organisms just really don't like UV at night, and that means we can kill them with a fraction of the dose that's required during daylight. Our initial trials targeted various powdery mildews because they're easy targets. They're on the outside of the plant. That makes them especially vulnerable to UV. But we've since found ways to use UV against other diseases and also insect pests. So I want to go back for a moment to the early 1990s, because I think this is a fitting example of just how far we've come in this research area. This is a tractor-drawn array of UVC lamps that our lab used in 1991 to suppress powdery mildew on grapevines. The UVC treatments were quite effective. They also defoliated the vines and made the grapes look a little bit like small russeted potatoes. To put it mildly, that wasn't the success that we were aiming for. Fast forward a mere 30 years, and we're presently on the threshold of an entirely new approach to controlling plant diseases. Now, we got there only because we have a much better understanding of the pathogen biology, pathogen ecology, and because of the pooled engineering and physics and manufacturing and photobiology expertise of the project team. The discovery of enhanced efficacy of nighttime UV was one part of that, but there were a number of other refinements as well. Strawberries are the crop where we worked out most of the bugs in the system. So I'll spend a little bit of time on strawberries before we move on to grapes. This picture shows the basic array that we developed for the UV lamps that we designed in 2016 for the first large-scale trials on strawberries. Over each row, there's a hemi-cylindrical array of 20 UVC lamps that are backed by polished aluminum reflectors. That densely packed array of lamps and reflectors provides a large number of reflectance angles. So dose of UV throughout that three-dimensional space under the array is very uniform, irrespective of the distance of a plant surface to the nearest lamp. Now, those multiple reflectance angles also mean there's improved coverage of the undersurfaces of many of the leaves and fruit. Now, this unit was operated at a commercial strawberry farm in 2017. The UV dose that we used was 85 joules per square meter. Now, joules is a unit of measurement that's not familiar to a lot of people. It's just watts over time. So if you think of a 50-watt bulb putting out a certain amount of energy, if it's putting out a total of 50 watts, so you're getting 50 watts per square meter, for example, if you get 50 watts per square meter for 1 second, that's 50 joules. Do it for 4 seconds, it's 200 joules. In this case, the dose was 85 joules per square meter, and the applications were made once a week, starting 1 hour after sunset. A tractor speed we used was just about 3 miles per hour. So this is a short video showing what it looks like underneath the unit during one of the nighttime applications. You can see the hemi-cylindrical banks of UVC lamps and the reflectors that are over each row of plants. The power for the lamps was supplied by a small generator. Now, this was a unit that we designed, but it was entirely built and operated by the farm crew at the research site. Now, the treatments worked very well. In fact, the dose of UV that was provided suppressed powdery mildew across the duration of the experiment that was substantially better than that was provided by the best fungicide treatment in the trial, which was a combination of Quintec and Torino. We also confirmed that the UV treatments did not reduce plant size for strawberry or reduce the yield of the harvested berries. This is a video of what we call the Dragon 2.0. This is a tractor-drawn unit in operation at a place called Fancy Farms in Plant City, Florida. It looks a little bit less like a runaway tool shed, like the first version. So you can see we're getting closer to a commercial production unit. We now have a large enough footprint in multiple crops that we've actually attracted the attention of equipment manufacturers. That was our intent. As a research group, we really want to get out of the business of building machines and get back to the business of discovery. That's really what we do best. So we've repeated and expanded the strawberry trials in Florida and elsewhere in North America and in Europe. Now, some of the most intense interest in the UV technology actually comes from the strawberry nursery operations. They're under tremendous pressure to reduce fungicide use because they need to reduce the distribution of plants that harbor pathogens that are pre-selected for high levels of fungicide resistance and then get planted out in fruit production fields. And so we're collaborating with some of the larger nursery operations for strawberries on both coasts of North America. So this is the largest unit we've designed to date, and it's presently being used at Keddy Nurseries near Kentville, Nova Scotia. It has 90 UV lamps arrayed in 3 separate 8-foot long arrays, and each one of those covers a 5-foot wide bed of nursery plants, and it can move up to 5 miles per hour. This is the one we call Smog, after the fire-breathing dragon from Lord of the Rings, if you're a fan of that. In addition to these tractor-drawn units, there are fully autonomous robotic carriages that can move UV lamp arrays in either field settings or in high tunnels. Our principal cooperator in this work is Saga Robotics. It's a Norwegian company. This image shows one of the high tunnel trials in Norway. The results from Europe, where they have even more severe problems with fungicide resistance and they have fewer fungicide options, have been pretty consistent. The UV treatments effectively suppress powdery mildew, and in most cases they perform as well or better than the best available fungicides. So I think we're beyond the point where we have to worry about whether or not this technology is going to provide sustainable control of strawberry powdery mildew. It actually works quite well. The Saga robot is called Torvald. It's an interesting device that takes our basic lamp array and allows us to adapt it to a variety of crops, including strawberries, grapes, apples, and even hops, by varying the height and width of the lamp array and the carriage. The Torvald robot is fully autonomous, meaning that where it's allowed by law, it can actually operate independently without a human operator. These devices are presently largely one-off custom-built units right now, and they're probably within a year of being commercially available either for purchase or as leased units with technical support. Like everything else that's being manufactured these days during a global pandemic, Saga Robotics is challenged with any number of choke points in their supply chains. So they're having difficulty keeping up with demand presently. Now, as I mentioned a moment ago, we're in the business of discovery, and one of the latest refinements in the technology has been the addition of UV reflective curtains to the front and back of the lamp arrays. Now, this takes a very special fabric. In fact, it's the same reflective material that's used in Navy firefighter suits. It's a bit pricey, but it can boost the UV dose by nearly 30%. and it provides even better coverage of the otherwise shaded parts of the plants under the array. That means we can go faster, and at the same time we're going faster, we're getting better coverage. And that kind of innovation in developing various mobile arrays of lamps is now occurring at several locations, both in the US and elsewhere, where mobile booms, tracked units, and these autonomous robotic devices are used to move lamp arrays within plant production structures, as well as in field plantings for a number of different crops. During the late winter of 2019 and 2020, about a month before everything hit the fan with respect to COVID-19, I was in the Pacific Northwest to work with Michelle at IAREC in Prosser, Washington, as well as Walt Mahaffey's group in Corvallis, Oregon, on designs for tractor-drawn arrays for wine grapes. And you can see how the hemi-cylindrical array has now been altered to fit something closer to a grapevine canopy. In 2019, we had operational tractor-drawn units in New York treating grapevines and low trellised hops. In 2020, we had 2 of the Torvald robotic units from Saga working in vineyards in the Finger Lakes region of New York. We'll do that again this year, and we'll have robots in Oregon and in Italy this year, and in California vineyards next year. Showing applicability of this technology across several crops is really how we get the attention of equipment manufacturers. It reduces the costs of producing such units, and we make new discoveries in biology that may be relevant to many different crops, different diseases and insect pests. And that goes especially for grapes. While these machines have a certain, cool factor, they're fun to watch. It's the research on epidemiology, pathogen ecology, and photobiology research that really makes them work. Otherwise, it's just a toy. The more diverse trials we conduct, the more we learn. You never know what you're going to see until you look. Here's one example from our grapevine work. This experiment in 2019 began with grape powdery mildew as the target, but we found that the UV treatments actually controlled sour rot better than anything else we were using. Now, sour rot is a complex mess involving bacteria, fungi, and fruit-feeding insects. We don't yet understand how UV is accomplishing this reduction, but the point is it was not only very effective, it was quite unexpected. We never would have thought that this would have had an effect. And neither did we expect that UV treatments would be effective at all against the grape downy mildew pathogen, as it really represents a challenging target. It's growing inside grape leaves and fruit, but lab assays showed that pre-treatment of grapevine leaves made them resistant to infection for several days afterwards. And this was the first time we'd seen disease suppression that was caused by UV increasing the resistance of the host to infection. Now, it's one thing to see an effect like that in a lab experiment. It's not always the case that you can reproduce it in the field. In this case, though, the UV treatments also reduced the severity of downy mildew in the vineyard in 2019. And that level of suppression was comparable to that provided by a fungicide standard. Again, we don't yet know how UV is doing this. Hopefully that's going to come later, but, and this is a big but, had we stopped in 2019, we would have been a lot happier because 2020 was a far more severe year for downy mildew, and in 2020, none of the UV treatments provided acceptable suppression of the disease. The UV treatments still worked fine against powdery mildew, but they just didn't have the degree of efficacy needed to completely control downy mildew as a standalone treatment. So obviously we have more work to do here. Now here's another example of an unexpected effect that is immediately relevant to many crops. Low-level nighttime doses of UV effectively destroy the eggs of various mite species that attack a broad range of important plants, both in controlled environments and in field production systems. This suppression has been very consistent, and the technique is now widely used in commercial strawberry production systems in the Netherlands, which are almost always entirely based on glasshouse production. The primary effect of the UV applications is on the immature and particularly the egg stage. We're just now beginning to investigate how UV treatments affect other insect pest populations. Now, some of you may have seen some recent research reporting efficacy of ultraviolet light against botrytis or gray mold. We haven't been able to reproduce those results in our trials, either on strawberries or on grapes. That doesn't mean it can't be done. It may just indicate that we have a lot more work to do with respect to timing of the treatments, dose, and interactions with environmental favorability and cultivar susceptibility. This graph shows one of the first trials we completed using weekly nighttime applications of UV to suppress powdery mildew on Chardonnay grapes in 2019. There are a lot of people now focused on this area of research, and it's the combined solution of all of these plant pathological, photobiological, and engineering issues that separate a usable, effective, and safe apparatus from that vineyard fryer that we first used in 1991. Now, I don't think UV treatments are going to be the solution to every problem. I do think we're at the stage where discoveries are occurring at a greatly accelerated pace rather than once every 29 years. And as we gain more experience with these trials, we consistently improve the performance of UV against powdery mildew to the point where it often exceeds or at least equals the efficacy of a number of fungicide standards. These are the results from last summer, showing the best performing of the UV treatments against grape powdery mildew on Chardonnay fruit. So we're often asked how long the dark period needs to be after the UV treatment. And we generally recommend 4 hours. 4 hours is optimal. In those instances where you're near the time of the summer solstice in midsummer, where the nights can be quite short, our results indicate you could still push those treatments out to about 2 hours before sunrise and still get more than half of the maximum efficacy of the UV treatment. In those situations where you're pushing the time of sunrise, we'd suggest that the last 2 hours of the treatment be made at a progressively higher UV dose to offset that decline in efficacy due to having less than 4 hours of darkness remaining. So this is a challenge, but it's manageable. We're also asked questions about the possible effects of UV on fruit appearance and finish. Of course, high rates of UV can russet fruit, as we demonstrated conclusively in 1991. But we're now using less than 10% of the dose that we used in 1991, and we've yet to see an effect on fruit finish. So you can take a good look at these Chardonnay grapes and try to figure out which ones are treated with UV and which ones are treated with a fungicide standard. We didn't find any differences in berry size, finish, berry number per cluster, total cluster weight, between the UV treated and the fungicide treated grapes. Likewise, last year there were no differences in soluble solid levels among the UV treated versus the fungicide treated grapes. So it does appear that right now we're operating well below a level where we would significantly damage the plants, but at a level that actually provides pretty good control of powdery mildew. Okay, so what can we say right now with a fair degree of certainty about the uses of UV on grapevine? Well, first, we're confident we can achieve excellent suppression of powdery mildew. We've done this on several other crops now, other than grapevine, and the results from grapevine have so far been pretty consistent. The same goes for mites. It doesn't seem to matter what a mite lays its eggs on. We can kill them with UV. Next, in a limited study, we've achieved good suppression of sour rot, which is also good news because we don't have much else that works well against this disease complex. And then there's downy mildew, where the degree of suppression seems to be dependent upon the severity of a particular year. That doesn't mean we can't use UV advantageously against downy mildew. It does mean that we need to be aware of its limitations under severe disease pressure. As for botrytis, we haven't seen any measurable suppression on either strawberry or grape, but we haven't given up yet. Now, as for the effects of UV on the vine itself, it does appear that even at our higher doses and most frequent applications, we're operating below a level of UV that has conspicuous, detectable, harmful effects on either the fruit or foliage. That's not to say that there aren't any effects that might show up later or show up in the wine that's made from these grapes. That's something that's yet to be learned. In a way, though, these conspicuous deleterious effects being absent, that's not really surprising, because that's what we've found in strawberries, cucurbits, apples, roses, tomatoes, hops, basil, and rosemary so far. In grapes, we've measured some gross effects, some gross responses rather on growth, leaf length, leaf width, shoot extension, net photosynthesis, stress metabolites, berry size, berry number, cluster weights, things like that, Brix levels. None of those responses indicated a harmful effect of UV, and there are obviously a number of benefits with respect to suppression of things that would harm the vine. So I kind of started this story with trying to describe just how many people are working together to move this research forward. I want to leave you knowing that this wasn't all my work. I did not do this alone. I had a lot of help from some very talented people, and here they are. So Laura Peterson is a former county agent in New York and now farms 600 acres of vegetables in the area. She's on our project advisory team. Eric Seidman, when he was my office mate when I was a graduate student, who knew that he would someday be the director of the National Organic Farmers Association? And there he is. He's on our project advisory committee. Arupalai Suthaparan is the PhD student who made the breakthrough discovery using the UV at night rather than daytime. Arne Stensfond is a fruit pathologist from Norway. He's part of the team there, the valued colleague for many years. Mariana Figuero is one of the top people working on photobiology in the United States. If you type her name into Google and light, she fills up the first 3 pages. Mark Ray is the director of the Lighting Research Center at Rensselaer Polytechnic Institute. He's been very important in most of the work. And then there's me. The guy standing behind me is Olli Myrna. He's a Norwegian strawberry grower, mechanical engineer, and inventor. He's also on our project advisory team. Rebecca Seidman married Eric, but she's also a professor of sustainable agriculture at the University of New Hampshire. She's on the project advisory team. Robert Seam is an epidemiologist at Cornell University, one of the principal investigators on the work, and also my former supervisor. Natalia Perez is a professor at the University of Florida and has led most of the work on strawberry. Her graduate student, underneath the array, working on his suntan, is Rodrigo Onofre. He's now a postdoc at Kansas State University. He was instrumental in doing most of the work on strawberry and powdery mildew. Lance Kittle Davidson is a research geneticist and grape breeder at our station here, working with USDA. He's my partner in crime in most of these studies that require expertise in molecular biology. Jan Nyrop is our director of the experiment station at Cornell, but he's also a very talented entomologist and leads the work on mites and UV. And then there's Walt Mahaffey and Michelle, our colleagues, valued colleagues working on the left side of the country in the investigation. So my principal role is really just to get you interested in this kind of weird mix of biology and epidemiology and technology. I want you to stay interested in it. I wanted to get you to ask some questions about it. So when we get to the period for questions, we'll see how well I've done. If you've made it this far, you've been a very patient and attentive audience, and I look forward to answering any questions you might have. So thank you very much.
Oh, thank you, David. So yes, there are some questions already. So the first is, what will the likely maintenance requirements be for a unit using the technology? For example, A typical fungicide tractor might run for maybe 750 hours per season.
Mhm. So the bulb lives are measured in thousands of hours and duty cycles. We have units that we've been using for 3 seasons where we have not had to replace a lamp, a ballast, or any part of the electronics. As for the robotic devices, I really don't know. We have used one all last season, and we started using it this season without breakdowns. That's a good question. I would look at the warranty that's offered by the manufacturers. So far, these are custom built units. The autonomous robotic devices are actually manufactured though.
Yeah, okay. And you mentioned best application is finished 4 hours before dawn, but is there a best time after dusk?
Really what you want to do is wait till the sun is below the horizon and then count off about another 30 minutes. It's called civil twilight. Once you've reached the end of that, it's dark enough that there is no interference from what little stray blue light might be actually still present. So
Okay,
half an hour after sunset.
okay. Will the power requirements allow for multi-row units?
Absolutely. So even smog, which has close to 155-watt lamps, is running off a relatively small generator.
Okay. Let's see. So you talked about the DNA damages. Whoops, they're coming in and moving my my screen here. Okay, you talked about the DNA damages on pathogens to explain the effects of the UV. In France, the Society UV Boosting developed UV light treatment in vines, talks about activation of plant defense by an effect on the jasmonic and salicylic pathway.
Mhm.
Do you notice this kind of effect, or do you think that it is also the effect is only effective on the pathogen and not the vines?
The plants do respond. I mean, you will see upregulation of phenolic synthesis in the vines, uh, but the primary effect with respect to powdery mildew is directly upon the pathogen. When we separate the pathogen from the plant, and you can really only do that with the spores of the pathogen, you see the exact same degree of kill off the plant that you do on. So it's these compounds do function in defense against some pathogens. They may indeed function against powdery mildews. But the doses of UV that we're using are more than enough to kill the pathogen on the surface of the plant without involving host defense.
Okay,
It may be that these are functioning against downy mildew
yeah.
because we're seeing suppression of downy mildew when the plants are treated with UV before the pathogen arrives, and that has to be due to altered plant susceptibility.
So is there any benefit in treating in the off season when there's no foliar growth, like diseases that can overwinter? And then what about decreasing the amount that can stay in buds rather than just the leaf and grape bunches? And
It's
then I'll
that
ask
would
you another question after that.
be a tough target. For one thing, of all of the structures that are produced by powdery mildews, it's only the overwintering structures, the Cleistothecia, that would be on the bark of the vine that contain melanin and thick cell walls, and those cells are dead. So getting UV to the living tissues inside of these overwintering structures is going to be very difficult. It's going to require very high doses and very high intensity. I don't think that's likely. Likewise, getting UV into a bud is going to be nearly impossible.
Yeah.
So no, I don't think it will. It of all the it has all of the characteristics of a bad and difficult target.
Yeah. And then do you know the approximate cost of this treatment versus spray regimes, the sort of cost effectiveness?
It's entirely dependent upon how you value your own time. The materials to build a single row unit is a couple $1,000s. The lamps are not expensive. They're hard to find right now during a pandemic, but the lamps cost about $10 a piece. A ballast can run 2 lamps, and the ballast is about $30. So you have to build a carriage and put wheels on it. But you could probably build one of these towable arrays for less than $5,000 if you did the fabrication yourself.
Okay. And what type of insect pests have you found success in controlling?
So far,
Besides mites. Only mites so far?
just mites so far. We've irritated thrips, which made me feel good.
We irritated leafhoppers, but they came back the next day a little very angry with irritation. And that's one of the things that the Wine Commission is actually funding as a part of Lexi's project is we're going to be looking at mealybug, early season mealybug crawler suppression.
The problem with insects is they don't sit still like fungi do. So they're much more challenging to get mortality data on because they don't die right away, especially the adults. So if it's a pest where a benefit is received by killing them the day after they're exposed, then that's great. But in the case of a leafhopper where the injury can be inflicted in a transient fashion and then the leafhopper is going to leave the area, then irradiating them and killing them after the damage is done, that's just revenge.
Are the commercial UV units drawn by a tractor or do they have their own engine? If the latter, are they autonomous?
There are no tractor-drawn units that I know of that are commercially available. These are all built by our collaborators.
Okay.
We do produce designs for the arrays.
But you're right at the cusp of really commercial manufacture yet.
We don't want to build things.
Right.
We want, if we could run a business without a subsidy, we wouldn't be scientists.
Okay, now here's a couple more. Are there any phytotoxicity issues that would need to be considered more than we do now if this was used in a hybrid chemical / UVC regime? Can you envision, maybe it could have a dual?
I do think that eventually we will get to some kind of an integrated program where chemicals are used in conjunction with UV. As I said, these are used primarily to date on high value crops with multiple pest systems. So it's not going to be something where UV controls everything.
Right.
But in an area like the Western United States where powdery mildew's really, your other options for controlling pests and diseases would be so much easier if powdery mildew was out of the picture. And
Right.
and I think UV has the potential to do that.
Okay.
And so maybe,
then-
can I follow up with Richard's question there?
Sure.
So Walt Mahaffey, his trials down in Oregon are doing that. He's using a hybrid system where he's essentially doing one spray a week with sulfur, and then the next other treatment is with UV and with various intervals. So he's working on that with sulfur. Ours up here is a hybrid system, but not within a spray program. It's splitting up the season, so it's UV, and then we switch to a chemical treatment. But Richard, to follow up with that, we do have to treat our entire vineyard with insecticides, right? So we do whole vineyard treatments and then a day, but we usually do then the day after our UVC treatments. That way we don't necessarily have that direct overlap where there might be extremely high levels of chemical residue on the leaf while we're using the UVC treatment. So that's just one thing we've done to, obviously it's a good test question, but to potentially avoid that for this trial, we do the UVC treatment and then follow up with an alternative spray second.
Yeah. And this is a strategy that we've employed successfully also in strawberries,
Okay.
where powdery mildew is a serious problem, but it's certainly not the only problem.
Right. And David, could you see this maybe being used after rain events to protect pruning wounds from eutypa or other dead arm, or are we going to get back into the cell tissue, the living tissue?
I don't think you're going to damage cambial tissue around a pruning cut with UV. So this is a really good technology for attacking single cell microorganisms at night. Multicellular organisms are harder to kill. That's why we have trouble killing adult insects. They have a thick integument. It's difficult to drive UV through that. Shortwave UV doesn't penetrate tissues very well. In fact, it has difficulty getting through the waxy cuticle of plants. So that is a benefit actually when you're trying to kill a powdery mildew, because the difference between what will harm the plant and what will harm the pathogen is quite large. So I don't know if this would be effective in a therapy for pruning wounds to prevent eutypa, but I do think it's not likely to damage the tissues around the pruning wound. not the plant tissues.
So Richard, I think the problem there too is, when we say if it rains after pruning wounds, that's when Eutypa is releasing spores. The problem is we don't actually know how long after the rain Eutypa starts to release spores. And so the question is like, would you go out and do the UVC treatment but even before Eutypa releases spores? So then it's going to provide absolutely no protective activity. It's purely an eradicant technology in that situation. So the timing, if we had better idea of when Eutypa was actually infecting the plant, both time of year, that's I don't think is very well understood in Washington, and then time after rain event, then probably, but I think that's a lot more just basic Eutypa biology that needs to be figured out there.
Yeah, in our area, the other thing I didn't think of until just now is we're doing our pruning in midwinter, and fluorescent, these low pressure discharge UV lamps are sensitive to temperature. Like a household fluorescent lamp, it doesn't perform very well in a cold environment.
Okay, well, that will affect us too. So can both of you maybe touch on the safety, worker safety and exposure? And are there standards that have been set yet, or are we still in that area where they will be developing?
Yeah, so these lamps look like fluorescent lamps. They're not truly fluorescent. At their heart, all true fluorescent lamps actually produce shortwave UVC inside, but they're coated with a phosphorus compound that fluoresces and gives off visible light. If you take away that coating on the inside of the tube and just have a clear glass tube that transmits UV, it's a low pressure discharge lamp, and it produces only UVC. These lamps have been around for 75 years. They're in a lot of applications. So the health and safety standards are very well established. These are used widely in hospitals, operating rooms, air purification, water purification. They have a lot of industrial uses. So yes, there are worker safety standards, and in the cases of the units that are used in agriculture, the PPE that's required is very similar to what you would use for pesticide application. So opaque clothing, no exposed skin, and eye protection are the most essential things. You do not want to have exposed skin around these lamps, even for a few seconds. And that's why the arrays that you see have those plastic curtains at each end. Those actually block UV. So we do have safety pamphlets that we give out to anyone who's involved in these applications.
Okay. I think we've answered all the questions. Yeah, let me check. Yes. Anything you might want to add, either one that you forgot to mention?
Yes, if you're really concerned about the effects of ultraviolet light on wine quality, epiphytic microflora, and quality parameters, you should keep an eye on what Michelle's doing.
Okay. So
she's the expert in that area.
So David,
there is a question on you, because you and I have talked a little bit about this, about using LED UV lights. Somebody wants to know about using LEDs because the less requirement for power and, pretty functional.
Well, they won't work as well, but at least they'll cost you more.
Oh.
No, that's a serious answer would be there. Present technology for UV LEDs is really underdeveloped. They're very expensive and they're very low powered. So right now we have almost the ideal tool. We have a 75-year-old technology that is really cheap and extremely powerful. So for an LED to match that, the LEDs are going to have to start putting out, instead of milliwatts, they're going to have to put out 50 watts, 100 watts. And they just can't do that right now. The materials that LEDs are constructed of are very sensitive to UV, so they essentially self-destruct. And they're frightfully expensive.
Yeah. So David, in your work with the grapes on the East Coast, you haven't followed it through the winemaking life cycle.
We have not.
Okay.
We would like to do that, but right now we're at the stage where we're really looking at efficacy against the diseases and as many different pests as we can suppress with them. We have not yet made wine with any of the grapes. we've looked at some of the basic kind of crude measures of whether it's harming the plant, and we haven't seen any indication of harm. But no, we have not yet made wine.
And that is part of Michelle's project.
No, we're fruit
Oh.
sensory. Yeah, we're doing
Oh,
fruit
fruit
sensory.
sensory.
Yeah, so
One-
up
one
to
step-
the first pad, up to the and a whole suite of much more in-depth chemical analysis on the fruit. So tannins, phenolics, flavonoid. I mean, we're really kind of digging into some of those other components, and then doing the fruit sensory. But we're not moving into the winemaking aspect until we can get a good disease control management out here.
Yes.
And you know, there's challenges with research level winemaking as well. So I think I'll probably, once we perfect things on our end, we will turn it over to the
Right.
industry to tell
That's
me how
that's
they
exactly
like.
that's exactly what I would do.
Mhm.
We'd take it one step at a time. Does it work? If it works, does it cause harm? If it doesn't cause harm, what's it do to the wine?
Right. Right. So it sounds like we still have several years of research in front of us, but I'm
It's
anxious
job
and-
security.
And if you're driving by the station on Monday nights or Thursday nights between 9 p.m. and midnight, you might see the thing glowing out in our vineyard here.
Oh, great. So with that, we're just a few minutes after 4, so we will wrap this up. Thank you, everyone, for attending. And as I mentioned, we will send out the recording link to all those who registered, and it will be posted on the Wine Commission's website.
Thank you, Melissa.
So with that, thank you very much, Michelle and David.
Thank you all.
Good afternoon, everybody. It's 5 o'clock where David's at, so I think it's
Yeah.
5 o'clock everywhere.
7 o'clock.
Past 5, you know what I mean.
It's after 5 somewhere.
It's after 5 somewhere. All right, thanks everybody.
Okay. Thank you.
Bye. Bye,
Bye-bye.
everyone.